Chapter 15 was all about optimizing functions and Lagrange multipliers. And in the first problem from chapter 15, section 1, we want to look at critical points and determine if they're critical points. And then if they are critical points, then classify them, and we're given a contour map. So rather than think about what this is an exercise mostly in reading contour maps and understanding what critical points should look like on a contour map. So let's take each point in turn. So the point A is sitting between these two contours, 3 and 6. The important thing to note is that the contours, A is between 3 and 6, and the contours are roughly in the same direction. So this definitely looks like A would be going up a hill towards 6. It doesn't look like there should be some kind of high point in between the 3 and the 6. Now, if we look at this from the side, and here we are at 3, and then going up this hill, it goes way up and then comes down to 6, that's just cheating. But it looks like A is on the slope of a hill, so A is not a critical point. A looks to be on a sloping hill. So not a critical point. It could be. If this was a 3 and a 3, then I don't know, that would be weird contours. We would need another contour in the middle. But it looks like if we draw a line from the 3 contour through the point A to the 6 contour, it looks like we're definitely going up a hill. If we imagine calculating the gradient at A, it looks like it should be pointing in this direction, kind of perpendicular towards the 6, because whatever value A is sitting on, it looks like that contour would be running parallel to the 3 and the 6, roughly parallel. So A, not a critical point, so not going to be a local maximum or a minimum. Point B is surrounded. Point B has one contour that's going around it. That's labeled 6. So this right here is a pretty strong indication that we might have a critical point at B, because this looks like it could be the top of a hill or the bottom of a valley. So this could be the low point in a dip or a puddle, or the high point on top of a hill. If we look at the surrounding contours, there's a 3 contour here, and then there's another 3 contour underneath it. We have to trace pretty far around this one. It looks like a 0, but the contour on the other side is also a 3. And that connects at the points C and D on each side. So B looks like it's sitting on top of a hill. So it looks like B is a critical point, and that it's, I would classify it as a local max. I went with a 90s extreme X apparently on this one. So if we think about walking around on this contour map, here we are between 3 and 6. We get to 6, and then if we had more details, maybe there's a 7, 8, and then there's a 9 when we get to B. It could be that this whole this is just a big plateau at 6, and they're like saying, haha, it's a big flat point. But even if that's the case, the derivative in the x direction and the derivative in the y direction looks like they're going to be 0. Also, if I say, no, haha, the critical point is actually over here where you couldn't see it, then I'm just cheating. in which case I was going to take the points away from you anyway. Any questions on point B? Reading that as a possible critical point and looking at the contours around it and saying it could be a maximum. We would switch over to a minimum if these 3s were instead, say, 13s, in which case we'd be at 13, drop down to 6, and then it looks like this is in the bottom of a depression rather than at the peak of a hill. All right. So point C is the other point in consideration. Point C is sitting at a place where contours are crossing. So C is in an interesting position. So point C is at a place where contours, there's a contour running through C this way, which is a 3 contour. And there's a contour running through C the other direction. So C is at this little cross of 3 contours. So the height of C looks like it's definitely going to be at 3. But we have to decide, is this at a peak, or is it at a valley, or is it at neither? Once again, we have to look at points up, above and below, and to the left and to the right. If we go to the left and to the right, we see that there's a 6 contour over on this side. And C is, we have the 6 contour over on this side. This is the hill on which B is sitting. So it looks like we got 6 down to 3 and then back up to 6. So there's kind of this valley in the X direction. But if we look in the Y direction, the next contour above here is at 0. And then the contour down here below is also at 0. So now it looks, if we go in the Y direction through the point C, we're going from 0 up to 3 and then back down to 0. So it looks like C is a critical point, but it's going to be a saddle point. In the X direction, it's a minimum, and in the Y direction, it's a maximum. C is a critical point, but it looks like a saddle point. It looks like it's a minimum in the X direction. But it looks like a local maximum in the Y direction. The difference between a local maximum and a global maximum is that the B is a local maximum because it's the highest point in this small area. If there are points outside in a small neighborhood around it. If we look at the entire, if there's some point not near B that is higher than 6, then B is not a global maximum. A local maximum is the biggest kid in the neighborhood. A global maximum is the biggest kid in the world. So it's the same as when we had this in single variable calculus. So if we had a function that on a region that goes like this, here is a local maximum because there's a small neighborhood around that point where that point is the highest, but it's not the highest point on the entire graph. So here could be a global maximum. It could be that the local maximum and the global maximum are the same. So if I look at a graph, if I just look at this region of a graph, here's the highest point. So in this case, this local maximum would be a local and a global maximum. Any other questions on problem 1? Great. Let's pause the video and look at some more problems.